some random Hamiltonians modeling superconductors.
What does the word Fern mean in this context?
Okay, do I get 2 extra minutes? Okay. Okay, so everybody who wants to talk to me about Fern is referred to the private question session after my talk. So I'd like to thank the organizers for organizing this conference. In fact, this series of conferences at this very beautiful place. I think that was a great idea to celebrate and to discuss Anderson localization 50 years after. I also appreciate that you came to my talk. Would appreciate especially the young student to stay here, but now he had to leave for some urgent reasons. Okay, what I would like to tell you today is some spectral theory for random Hamiltonians that arise in the theory of superconductors. And this is some work in progress with Bernd Metzger, who is now in Paris, and Peter Müller, who is now in Munich. And nothing is written up, so there might be some improvements in the futures, maybe some assumptions missing in my talk, and so on. So this is really not written up, work in progress. So we start with what I call an effective BCS Hamiltonian that comes from Bardeen, Cooper, and Schriever, who I think were the first to explain superconductivity from a theoretical point of view. The idea is that you start with a Hamiltonian that contains a two-particle interaction. So this part is just the one-particle Hamiltonian, and then here you would expect a quartic term which describes the interaction between the particles. Now you see this is not here. Instead, let's first shortly discuss what I call the Hartree approximation. I don't want to bother about Fermi or boson statistics, so I take in distinguishable particles. So what you do in the Hartree approximation is you average out pairs of creation and annihilation operators in the quartic term, and you get an effective one-dimensional Hamiltonian that you hope describes to some extent or approximates to some extent the n-particle, the interacting n-particle system. Now what you do here is, instead of taking a pair of a creation and an annihilation operator and average this out, you take two creation operators, average them out, and two annihilation operator, average them out. So what you get is an operator that does not keep the number of particles fixed. So here you go 2 steps down, so from n particles you go to n minus 2 particles, and here you go 2 steps up. And the physical idea behind this is the formation of Cooper pairs. That is, you have two electrons that interact very strongly in an attractive way, form a Cooper pair, which in this description leaves the scene. So the Cooper pairs are no longer described in this system, but you describe what is left. So this means you destroy 2 electrons, which means you build a Cooper pair, and here a Cooper pair decays into 2 electrons. Now this BCS type operator can be written in first quantized form because in fact there is no interaction between particles left. And you write this, or I write this as a 2x2 block matrix where the A obviously comes from the A k prime, and delta prime come from these terms. So I call this matrix operator boldface H. A is a self-adjoint operator, and in the case I consider, it has real entries. Otherwise, I would need a transpose in the lower right corner. So I have a self-adjoint operator with real entries. In physical terms, that essentially means there is no magnetic interaction involved. And the A describes the motion of a particle, let it be an electron or a quasi-particle, and minus A describes the motion of a hole. And B sort of is the interaction between the hole and the particle, where you should not take interaction too literally, because this is not a two-particle system. This is a one-particle system where the particle can decide to become a hole. So it can convert to a hole, which means there is a Cooper pair formed, which again leaves the scene then. Okay. Now, this is a more formal description. I will have as my basic Hilbert space H1, L2 of ZD. Most of what I do, at least at the beginning, would also work in capital L2, but this is a bit easier to describe. And the system composed of particle and hole is just, the state space is H, which is just the direct sum. And the vectors in H I conveniently write as vectors psi1, psi2, and this corresponds also with the notation of the operator as an operator valued 2 by 2 matrix. So the motion of one particle is governed by a Hamiltonian, which has this form. It's H0, which is the actually in most cases the discrete Laplacian. Then I have a potential V and a constant E0 that, of course, I could just absorb in the potential, but it's in some ways convenient to keep it there, because in some sense it represents the Fermi energy or the chemical potential. So my H0 is this discrete Laplacian. So I have the diagonal removed, which means that its spectrum starts at minus 2D and goes up to plus 2D. B is a potential which may be random or maybe something else. And then the motion of the hole is governed by minus H, just because in a sense the hole has negative charge and quote-unquote negative mass. So if I have so the dynamics of a system particle hole is just given by this block diagonal matrix, and the B in the off-diagonal terms is a kind of a hopping term that means describes the way a particle can convert into a hole and vice versa. And in this talk, B will always be or almost always be a symmetric operator, and in fact it will be diagonal because that makes life a bit easier. So B is a diagonal operator, but of course not necessarily a constant multiple of the identity. Sometimes I will be talking about
diagonal in L2, a function.
I mean a function, yes. So I mean, since I have small L2, this is, I call it diagonal, yes, but it's a multiplication operator. Now, sometimes I talk about eigenvalues of H, which may not exist because that's a bounded operator on a infinite dimensional Hilbert space. What I mean then actually is cut this system and just consider it on a finite subset lambda of ZD and look at this operator. Of course, when you define the density of states, for example, you will use this operator. Now, one remark about symmetry classes are not the most general, but a more general BCS type matrix has this form, and this in the notation of Altland and Zirnbauer is an operator of symmetry class C. So we have this transpose here, and A is a complex self-adjoint operator. And B is a complex symmetric operator. So it's symmetric, but if you do the transpose, but not the complex conjugate. We will most of the time work in what Zirnbauer calls the class C1, which is this. B and A is real and symmetric and therefore self-adjoint. Okay, let's first talk about the spectrum of these operators as a set. What is useful to realize is what is called particle-hole symmetry. That is, if you conjugate the operator with this unitary matrix, then you get minus the operator. This U here converts particles into holes and vice versa. And from this we learn that the spectrum of H has to be symmetric around 0. Moreover, it's useful to square the operator. You get on the diagonal something that looks very nice. It's H squared plus B squared. Of course, here we have this the operator H is neither positive or negative because it's the spectrum is symmetric around 0, while this term is obviously positive, and here you have the same term. Of course, what's not so nice is the commutator here, and we will soon assume at the beginning that this term vanishes, because then you just have H squared in diagonal form and life is easy. So the spectrum of H then is given as the set of all, of course, real E, such that E squared is in the spectrum of H squared, just due to the particle-hole symmetry. Okay, let's start with the simplest case, that is B is actually a multiple of the identity. I allowed myself this abuse of language. Then, of course, a square is a diagonal matrix. And therefore, you can reduce the spectral theory of H to the spectral theory of the non-boldface H. And here's the easy result. The spectrum of H then consists of these values. You take any eta that is in the spectrum of the one particle, the particle H, square it, add B squared, and take the square root. And then you symmetrize because plus and minus this term has to be in the spectrum. And what you see is that this spectrum has always a gap between minus B and B, independent of what H is. This is considered to be typical for semiconductors. They at least, superconductors. Thank you very much. For superconductors, because it's very typical that you have a gap at 0, which sort of prevents the Cooper pairs from decaying. Okay, of course you learn more of this if you take eigenfunctions of H, or if H does not have eigenfunctions, then you restrict and you take this this finite dimensional matrix. Then we saw that these are the eigenfunctions of the 2x2 H, and of course the eigenvalues, and the eigenfunctions are given in this way. So you take the eigenfunctions of the particle H and multiply it by a certain number mu n, which I have written down here, and this is just the eigenfunction. Okay. By the way, you see also that if you apply the particle-hole symmetry to this, you get this operator. You get this vector. And for later use, I would like to note that the following is true. If you have an eigenfunction of h with, say, eigenvalue e, then the scalar product between the first and the second component is positive if the energy is positive, and it's negative if the energy is negative. This is, I mean, just from simple calculation, but that will play a role later. Okay. Now, what can we say if B is no longer constant? That is, you have in the off-diagonal term, the quote-unquote interaction between particle and whole is diagonal but not constant. Then it's not so hard to see that if B is bounded below by some beta, so B now is actually Bi, I runs through ZD, it is bounded below by beta, which is which is positive, then H square is positive. And in fact, it's bounded below by beta square, which means that this operator H again has a gap between minus beta and beta. Now this seems to be completely obvious by monotonicity, right? You just decrease the values on the diagonal of the off-diagonal term, and you expect that this is going, then the eigenvalues are going down, well, we'll see they are not. Okay, here's a remark. Again, this is completely independent of the choice of H. I mean, H could be, for example, a GOE random matrix, and still it's true. Right? It may have the point E equal to 0 in the spectrum or not. Okay, here is the warning about monotonicity. You might expect you get monotonicity in BI. And if you had that, everything would be pretty simple, but monotonicity is wrong. So I have two arguments, one not so convincing and one convincing. Here is the not so convincing argument. You see, if you square H, boldface H, then you get these nasty commutators. And the commutators contain differences, Bi minus Bj. In fact, on the subdiagonal. And you might expect that this may cause problems for the monotonicity. Now, the more convincing argument is this. I just computed the eigenvalues. This is a 100 by 100 matrix. So we start with all the b's equal to 1, and then we increase the odd ones from 1, which is here, to 2, which is here. And these are the first 6 positive eigenvalues. Of course, there are also negative ones. And you see that the first positive eigenvalue goes slowly down. In fact, you can also have situations where it is constant. In fact, if the dimension of the matrix is odd, it's always constant. If it's even, it's decreasing. The next one is increasing. The next one is decreasing, increasing, decreasing, and so on. Right? And of course, if you follow the eigenvalues correctly, then this is increasing and decreasing again. This is decreasing and increasing and decreasing. So it's all a mess from this point of view. And I was actually disappointed when I printed this. Nevertheless, this result is still true. You have always a gap. But you don't have monotonicity of the eigenvalues.
Maybe I can make a comment. Since this is a program of Anderson localization, it's maybe worth mentioning that this statement that even if the gap function has this order and there's also random potential,
it's called Anderson's theorem.
If the gap persists, it's called Anderson's theorem.
Yes. Thank you very much for this comment. Right. So, in fact, there was a belief that randomness in the diagonal term, that is the H, would might destroy the gap. And the result is it doesn't. In fact, the gap doesn't see at all whether there is randomness or not in the H. That brings me to the point, what about making B, which is the off-diagonal, the interaction part, random? Okay, let's suppose that B, still diagonal, still multiplication operator, consists of independent, identically distributed random variables, and let's P naught call their common distribution measure. Then the result is the following. If the support of P naught is just an interval from B min to B max, and B min is positive, in fact, I probably don't need this, then the spectrum of H is again given as if you have a constant diagonal. You take each beta in this interval B min, B max, and square it, and at eta square an eigenvalue or a spectral value of H, and take the square root. Now, this is, of course, something that you know from the old days of Kunz and Suyar. Here again, it's a bit more tricky because you lose monotonicity. And in fact, for the Anderson model, this is true if support P naught is any set. This is probably wrong here. At least I can't prove it. However, if the diagonal operator, that is H, is actually H naught, so there is no random potential on the diagonal, then it's true for any set support P naught. Of course, it's clear for this audience, I suppose, that this is just a statement about the spectrum, and it doesn't give us anything about eigenvalues, about eigenfunctions, about the measure theoretic structure of the spectrum, and so on. Okay, so far for the spectrum. Let's now talk about the density of states. Here is a brief definition. Let's go through fast. You take a finite subset lambda of CD, you restrict your operator there, then you have a finite matrix, you count eigenvalues and order them. Here's the ordering, and of course you repeat them according to their multiplicity, and then the integrated density of state n of E is defined to be this limit, where the limit is understood in the sense of weak convergence of the corresponding measures. Actually, it's weak convergence in this context. And if this distribution function n, or the corresponding measure, which I call nu, has a density, I call this little n of E. And this is then the density of states, or this is the integrated density of state, and the corresponding measure I call the density of states measure. Let's start with constant B. Of course, you can compute the density of states for, well, of course, you have the idea that you could compute the density of states for the case where B is constant. And in fact, here it is. So the density of states, if the density of states for H exists, then the density of states for the matrix operator H exists as well, and it's given by this term. Of course, it's 0 in the gap, as you expect, and it's this expression outside the gap. Now, this term is certainly not at all surprising. N naught is the density of states for the particle operator H, and you do some square rooting and squaring here. But what I think is striking in this, of course, well-known formula is that you have a part in front of this, which of course is just the Jacobian, and this has a square root singularity at the point E equal to B. And that means that for this this case where B is a constant, that at the internal boundaries of the spectrum, the density of states actually explodes. It's not bounded, and it doesn't help at all to put randomness in the diagonal term, right? So, I mean, we all, well, at least I first tried to prove Wegener until I talked to physicists who know this formula, of course, right? I mean, I immediately think one should be able to prove Wegener here, get a bounded density of states, but that's just wrong. So here's a picture. This is the density of states for B equals 0. In fact, I'm a bit cheating. This is not computed. This is just the normal distribution. And this is the case B equal 1. So in some...
It should be Wegener if you use the right variable at the edges. Right? You're demanding it be Lipschitz in E, but you really want to demand it be Lipschitz in some suitable square root that has this singularity, and then I would expect it.
Yeah. Yes. Yeah. So, in other words, so see this h square.
Or if you want h squared.
Right. H square, you have Wegener, but because you have to take a square root in between, you end up with this. Anyway, if you want to prove a localization, you can do it that way. But of course, we know the eigenfunctions. If H has complete localization, then the Wolfers H also has complete localization. Right. Anyway, this is what happens to the density of states. It gets sort of ripped up at 0 and pushed outward, and it stays as, in some sense, it stays as the states stay as close as possible to 0. So they accumulate in some sense here. What about random B? So again, we put B random on this in the off-diagonal terms, and as you might expect, for this you can prove Wegener. So let's see at the assumptions. P naught is the common distribution of the IID random variables Bi, and I assume that P naught has a bounded density. B min is the inf of the support of P naught, and I need this to be positive. I will comment on this later. Then the density of states n exists and is bounded. In fact, I get the usual Wegener estimate. And from this, you can also try to prove Anderson localization, for example, for high disorder for this
This
kind
supposes
of
P naught
operator.
has a bounded density.
Pardon me?
This supposes P naught has a bounded density.
Yes.
Oh, it says it has a bounded density. Just can't read it.
Okay, good.
Just listen.
At least we agree. I'm happy about this. Okay, so from this you can do, for example, multi-scale analysis with this operator. Here's the idea of the proof, and I want to give this because it has a peculiarity which again has to do with the non-monotonicity of the eigenvalues. So let's work in some fixed finite set lambda. We suppose we are looking at a positive energy. Then we know already if we increase some of the Bi, this might increase or decrease the eigenvalues. However, if we increase all of them, which is essentially expressed by this gradient, so this is the nth eigenfunction derivative with respect to the random variable Bj, then you end up with something that is essentially the scalar product of the two components of your eigenvector psi. Maybe you see that this is positive. I don't. I mean, in the previous case of where the B was constant, we knew exactly how it looked like, and this would just be mu n, which we could compute. But here, we need some control on these scalar products. And this is provided by the lemma. Suppose you have an eigenfunction with eigenvalue e, which is positive. Then the scalar product between the first and the second component is just this. Now you see on the right-hand side, you only have scalar products between psi1 and itself, and this should be actually psi2, I'm sorry. So this is the scalar product in the big Hilbert space. And of course, it's always positive if B is positive, and the energy, as I assumed, is positive. In fact, the formula is also true if E is negative, except that, of course, then the whole thing is negative, because you have a negative term here. Now, for Wigner, what you need is that this is uniformly bounded away from 0, for which we need that the B is uniformly bounded below, that is B min is positive. That is the part where we cannot prove the Wigner estimate if the coupling on the off-diagonal term can be 0. I'm deeply convinced that it's true there, but at this point I just get stuck with the proof. So we know it's the density of states is bounded as long as B is strictly positive. Okay, here's something else. Of course, you might ask whether there are Lifshitz tails in at these internal boundaries. So far, we cannot prove that in a general case. But if the operator H has no diagonal term, this is just H naught, we can prove it. Right. So again, if B is not random, you have no chance, because there are not only no Lifshitz tails, but the density of states is exploding. But for random B and no diagonal term in the particle operator, we have this result now. Here I should say the following. I believe that our proof also works if B min is 0, but I'm not through checking all the details. So what I claim is only it's true for positive 0. But again, I'm pretty sure that it's true for 0 as well. So how does this work? Well, again, we have the problem of monotonicity. So what you do is the following: consider this unitary matrix and conjugate H with this. Then what you get is that you just interchange the B and the H naught. So you have B and minus B on the diagonal, and you have H naught on the subdiagonal. And then what you do is you look carefully at this operator and interchange columns and rows and realize that this is a guy you know already, at least sort of. So here is an example 4x4. This is this operator just as a 4x4 matrix. And the first thing you do is you interchange this column, and you get this. Next thing is you interchange this row, and you get this matrix. And then if you look at this carefully, you see that this actually is a direct sum of two Jacobi matrices, or of two Anderson models. Except that what is a bit strange is here you have the random variable B1, and here you have the negative. And if you continue, you have B1 minus B2, B3 minus B4, and so on. So it's alternating between plus and minus. And in the lower corner, it's also alternating, except that it starts with minus B1 plus B2 and so on. And this trick works not only in one dimension, but also in higher dimensions. So what you're left with is the following lemma. This matrix operator that we're interested in is actually unitary equivalent to a direct sum of two Anderson-type Hamiltonians. And these Anderson-type Hamiltonians unfortunately have alternating random potential. And the only thing you want to do, or you have to do, is prove Lifshitz tales for these operators. Well, of course, we know quite a number of proofs for Lifshitz tales, but this one is a bit out of what people have looked at before, because that's very peculiar, right? So, first thing is, of course, you have to deal with internal Lifshitz tales. Right. The second thing is, we don't have monotonicity of the eigenvalues, even in this for this operator, because if you increase B, then you might be at an even site, and that means you decrease the eigenvalues. So if you increase B at an odd site, you increase the eigenvalues. And of course, if you do it at simultaneously at various sites, you have no control of at all. Okay, now we also believe that we can do the case B min now, but as I said, details have to be checked. Here is why I strongly believe that it's true for B min equals 0, because here is a picture. This is an average of 100 matrices of size 3000 by 3000, probably a 6000 by 6000. It's amazing what you can do on a laptop nowadays. And V is uniformly distributed. Okay, V is 0, of course, and B is uniformly distributed between 0 and 1. And you obviously see at least something happening here. Right. Okay, so I think I displayed all my transparencies. At the end, I would like to just to tell you how odd these operators might be. I would like to sort of ask you the following question. Suppose you have the following operator. You have H naught and minus H naught, as we always had. And suppose that the off-diagonal term now looks like this. You have zeros. You have plus 1 above this diagonal and minus 1 below. I call this B. And here, of course, you have B transpose. Have any guess what the density of states of this guy looks like?
Well, the gap should close.
Yes, this is something I was deeply convinced of.
Well, I don't quite understand what the basis is. In physics, we know that if the superconductor is D wave, in other words, this thing is now not local. I mean, I see that you're not putting it on a diagonal.
Yeah.
And physically, I would say there's a Cooper pair, and it can now be elongated.
Yeah.
So it defines an axis, and now as I rotate this axis, after rotation by 90 degrees, the matrix element has changed sign. And then by 100 it has returned. This is called a D-wave superconductor.
Yes.
For that case, the gap closes.
That's right. But this is not exactly a D-wave.
Okay.
Right? A D-wave superconductor, I mean, what I was talking about when you have a diagonal is usually called an S-wave superconductor. a D wave usually has, at least as far as I know, is for D equal 2. And you have, here you have H naught in the first variable, tensor 1, minus H naught in the second variable, tensor 1. And it looks a bit like this, but it's not the same.
But it's a skew symmetric matrix.
That's right, yeah.
Well, that is like a P-wave superconductor would have a skew symmetric.
Okay.
Yeah, the gap can also close, it depends.
Okay, now the result is if you diagonalize this matrix, it looks like this. No, it's 2, sorry. Okay, no, sorry, it's 4. I'm sorry. So if this is H, this is H squared. That means that this guy has has only two values in its spectrum, and in fact they are infinitely degenerate eigenvalues. Right? I mean, this is something you would not expect. I just came up with this by computer experiments, and it certainly is a warning that it's not so easy to deal with these guys as you might think from the beginning. Okay, let me close by remarks on D-wave superconductors. We try to work on this as well. It seems...
So H0 here is just the standard ones off diagonal,
Yes.
zeros in the middle.
Yes. Yeah?
This property is not true if you replace B with the same form except that 1 is not a constant, right?
Yes.
Correct.
Right?
Yes.
If
This is very
for a
particular.
special value 1, right? It's
This
because,
is very, very particular, but I mean, I'm not saying it's describing anything in physics. It's
no, it's just because 1 plus I and 1 minus I, the product is equal to 2, and the inverse
yes,
except to the square root.
yes, absolutely. I mean, the only thing I want to say with this is be careful with these guys. It may be very different from what you think. Now, for D-wave operators, D-wave superconductors, you have for B, you have a term like this. And as Martin said already, for them, the gap closes. At least if I have H naught here, but I'm pretty sure that a random potential here wouldn't change anything. But the big question is, how does the density of states behave at 0? Again, we are working on this, but I don't dare to make any guess. So thank you very much for your attention.
Yes, Werner, could you come back 2 slides, I think it is.
Sure.
Yeah, thanks. Here, the B, if I got it well, is a diagonal matrix, right? B is diagonal.
Yes.
And the entries are random variables. And what you note by -1 to the n is that you have a flip sign. You multiply by a diagonal matrix, which
Yes.
is +1 -1.
Yes.
Okay. But then I don't understand why Lifshitz tails is a problem, because if you look at your single sites, right? What you have is you have random variables which are not identically distributed, but are still independent.
Yeah.
Right? The distribution as random, you just change, take omega I and minus omega I.
Yeah.
So they are distributed differently, but they're still independent from each other,
Yeah.
right? To know where the minimum of H plus or H minus is the spectral minimum, you should essentially, because as a function of these new random variables, I just had the -1 to the n disappear. This is again monotonous. So to look at where the minimum is sitting, you just should minimize the omega I and the minus omega I, right?
Yes.
And then you get a nice periodic configuration which depends on the support of your omega i's.
Yes.
And for this one, you can, I think, use the standard techniques for internal Lifshitz states.
Yes, this is exactly what we do, except that you have to be sure that in between nobody crosses the gap. And that's not completely easy to see. you know, the points where B is negative, you have to decrease the potential, right? And somehow you have to be sure that in this process there is no eigenvalue that comes from,
But I mean,
the upper band down.
isn't this just a continuity argument, the usual one, in the sense that you take the support of your B to be connected, and if something would cross, you will have something in between inside the gap for the spectrum?
Yeah, but how do you know this guy has a gap?
But this depends on the values of your B, right? Of course.
Yeah.
I mean, this is something.
And anyway, this is essentially what we do.
Okay.
To prove that there is a gap, we actually go back to the matrix operator. There you can see that the gap is there.
But my point was just to say that actually this is not an operator with, let's say, non-monotonous. It is monotonous. You just have to take the right random variables.
Right. Okay.
It's a monotonous operator.
I mean, yeah,
in the sense that if you change the name of the variables, you vary monotonously with respect to this. It's just.
You said you have no Werner estimate, no density of state bounds
for what?
for the off-diagonal randomness.
Okay, for the off-diagonal randomness, we have this. So okay. As you saw from the explicit calculation, there is no Werner estimate if the off-diagonal part is constant, right? Because the density of states is unbounded.
Some local bounds away from the
Right, right. Now, if B is random, then we have Werner estimates. But what we need is that 0 is not in the support of P0. For what I believe is completely technical reason, but we can't get around this at the moment. So this is in the sense that the thing we are trying to improve.
It's connected with your not having Lipschitz tails yet at 0. Because really the Lipschitz tails
Yes.
are defeating the singularity of the...
That's true, but the Lipschitz tails we have only if there is no diagonal disorder.
Right.
Because this rearranging of the matrix only works if the diagonal of H is 0.
The B should also be solution of the gap equation.
That's true.
And you are omitting
Yes.
this self-consistency.
Yes. I'm completely omitting the self-consistency question. Of course, B should come from the original operator. I completely admit this. We simply ignore it. B is for us an independent quantity, and I agree you should get it out of the self-consistency equation, but that we can't do. Period.
Thanks, speaker again.